Ladies and gentlemen, our next speaker, Jeff Hawkins, is well known as creating some of the icons of the digital world. Not that one. The Palm Pilot, the handspring Treo. These little devices that we all carry around with us now. Little did we know that he's always been just a part-time entrepreneur. He's done all this while his mind has been engaged in a little problem on the side called the brain. And for the last 3 years, he's run a neuroscience institute. And now he's going to come and tell us a little bit about his thinking about the brain and a new venture he has called Numenta. Ladies and gentlemen, Jeff Hawkins. Thank you, Jeff.
Am I on? And it's a pleasure to follow Nicholas. I thought that was a very inspirational talk on his part. And, you know, I do have these two parts of my life, and I have been designing mobile computers for 25 years. Back to the very original laptop, the Grid Compass, and up to most recently I've been designing the Treos and so on. And it's interesting because part of my motivation in doing that, certainly part of the motivation in forming Palm 14 years ago, was the belief that computers were too big, too expensive, too complex, took too much power, and that how are you going to get a lot of people on the planet to have access to computing technology? You're going to have to build small, reliable things. We've taken a different approach than Nicholas is taking, which he's taking this education approach, but I think it's very admirable. But as Bob just mentioned, I really have two parts of my life. And I really have been a part-time entrepreneur. Even when I started companies, I generally work part-time as part of my employment contract. And my main passion in life, although mobile computing is a big passion in my life, my main passion is actually understanding how the human brain works. And I take this very seriously. This is not a hobby of mine. And it's involved at various times, going back as a full-time graduate student at Berkeley in the 80s, until, as Bob mentioned, I formed and run a neuroscience nonprofit neuroscience research institute called the Redwood Neuroscience Institute for the last 3 years. Now, my specific goal is to understand the human neocortex, or the mammalian neocortex, and we've made a lot of progress in that. Quite astounding progress, actually. And a year ago, I published a book called On Intelligence, which proposed a sort of overall theory about what intelligence is and the biological mechanisms underlying it. It was more of a biological theory in that book. And that book it's been very well, and it's got quite wide acclaim in certain circles. Not everyone ascribes to my theory, but quite a few people do. But since when I wrote the book, and I stopped writing about a year and a half ago, there was quite a few things I didn't understand. I didn't have a mathematical formalism for this theory. It was really a biological theory. And we didn't really know how to build it, which is one of my goals. And working with a collaborator named Dilip George, who was at RNI, over the last year and a half, we've accomplished that. We have a very strong mathematical formalism for this now. We've built systems that work on the same principles as the neocortex. We've proven that this theory works. And earlier this year, we formed a company called Numenta. And I actually thought about whether it should be a nonprofit or a profit. And we decided to go for the profit route. And I'll explain why at the end of my talk. But one of the goals of Numenta is to develop this technology and get it infused in a lot of industries and a lot of research labs and get a lot of people excited about it. So I'm going to tell you about that today. Now, I just stood up here in front of you telling you I figured I understand how the human brain works, or at least the neocortex works. I understand it mathematically, and I know how to build it. Those are pretty broad claims, and you might be a little skeptical. I am not one, if you know me, I'm not one for self-promotion and hyperbole and so on. But those are pretty broad claims. I have 45 minutes here in this talk, and I can't possibly cover all of that. And I've decided to do a little different talk than I've done in the past. This is not a neuroscience talk. In the past, I've done a lot of neuroscience talks. I decided to do a technology talk, and I'm just going to describe this technology to you. And I'm not going to make an effort to prove to you that this is how brains work or this is what brains are doing. I'm just going to state that and focus on the technology, and that's what I think I can accomplish in this 40 minutes that I have remaining. We call this technology hierarchical temporal memory. It's not a really great marketing slogan, but it's very descriptive, and I really wanted to downplay it. I basically want to say this is exactly what it is, hierarchical temporal memory. I'll refer to it as HTM throughout my talk. Occasionally I'll slip back into the long version. And now let's get into it. Now I'm going to start with a little bit about brains, just a teeny bit. I brought my brain model with me here. I carry this around with me all the time. It's a plastic brain model. And this is about the size of a young adult's brain, a human brain. And if you were to look at the human brain, about 50% of it is dedicated to the neocortex. 50% of the volume is neocortex. And generally, it's just the wrinkly part on the outside. The old part of the brain, the other parts are kind of shoved up inside like a post, and this wraps around it. Now, the neocortex is everything you think about as intelligence. It is where high-level vision and hearing and somatosensory or touch occurs, where you generate all your high-level motor planning. It's where you think. All of your memories of the world that you can tell me about are in your neocortex. It's where you do math and planning and art and music and so on. It's all in the neocortex. If you take that out of your body, which I wouldn't recommend, but if you did, and you ironed it flat, it would look like this dinner napkin. It's about 1,000 square centimeters, about 2 to 3 millimeters thick, contains roughly, no one really knows, but roughly 30 billion neurons, somewhere north of 300 trillion connections between those neuron synapses. And this is you. My neocortex is talking, and yours is listening right now. We do know the fact that the neocortex has differentiated areas. There's parts that are for low-level vision and high-level vision and hearing and math and so on and face recognition. And a lot of imaging studies he's done, you see them in the news all the time. Scientists have discovered, what part of the brain is active when you play Scrabble or something like that. But what's really remarkable about, and this was discovered 25 years ago and first postulated by a guy named Vernon Mountcastle, is that even though there's different regions that do different things, so there's vision areas and hearing areas and so on, they all seem to work on the same principle, that there's an architecture in the cortex which is very fine. It's this layered architecture of different cell types, and it looks pretty much the same everywhere. And the hypothesis, which about half of the neuroscientists in the world believe, and half of them just not really can't quite believe it, is that the way we do all the things that we do is really built on the same principle. This is a fact as far as I'm concerned. I think I understand that principle, and I think HTMs are that principle, and I'm going to explain to you how that works right here. So I'll go back to my little slides. I need to define the area, and we can bring them back up on the screen. I'd appreciate it. Slides on the screen, please. Thank you. The area that we're dealing with, and this little picture shows it to you. On the left, we have the world. That's my PowerPoint version of the world, that little box. And in the world, there are things. We have people, cars, buildings, and so on, words, ideas, and songs. On the right, we have a cortex, a brain, or we might call it an HTM. And the brain interfaces the world through a set of sensors. That's the only way it knows about the world. Now, we tend to think that humans have like 5 senses. It's not really true. Even vision, which you take the retina, it's really like 1 million sensors. We have 1 million light sensors. They're arrayed in lined in an array. There's no part in the brain which looks at all of it. It's really, truly, you have to think about 1 million little sensors. By the time it gets into the brain, it's not a picture anymore. It's not like that. We have about 1 million fibers coming from your optic nerve. You have 1 million fibers coming from your spinal cord, your somatosensory senses, and about 30,000 from your ears, your cochlea. And that's the interface to the world. That's the only thing that the brain knows about. And when it gets to the brain, it's all just these little patterns on these axons. It's these little spikes that are coming in. They all look the same. The patterns coming from the retina look exactly the same biochemically from the patterns coming from your ear, etc. Now, I'm going to find a couple of terms here. These are the terms that probability theorists use, and they're really good words. And so I'm going to, if you're not familiar with them, I'm going to use them through my talk. We're going to call the things on the left causes. The things in the world are causes. What is a cause? You might think about if you were a brain looking at some pattern coming in from a sensory organ, you'd say, what is the cause of this pattern? I'm not particularly interested in the pattern itself. I don't really know. I don't really care what's on the retina or what's on the cochlea in the ear. I want to know what's causing it. I want to model and understand the thing out there in the world, not just this sensory sheet I have in front of me. Now, causes are things that are persistent. That's their definition. If you want to say, what is a cause? It's a persistent thing in the world. If it isn't persistent, then we don't care about it. We only care about the things that continue over time. And notice here that not all things in the world, not all causes are physical things. Words are causes, ideas are causes, songs are causes. They're just persistent patterns in the world. On the right, what we want to create in the brain, what the brain does create, and what we want to create in an HTM, is we want to build a representation of those causes. We want to have a model of the causes in the world, We want to have some way, a variable or a number or an activity on something which represents the causes in the world. And then we want to assign at any moment in time the probability that that cause is out there actually I'm interfacing with it. And so it's a probability distribution over causes. And we call those beliefs. The beliefs is the state of the internal representation of causes. So I might be looking at an animal and I say, I'm pretty sure it's a dog, but it might be a cat. I can't really tell. It's a kind of funny looking dog, and it might be something else. And so you have these multiple beliefs going on at once, but I'm pretty certain it's not a car. So that's going to be a very low probability. Okay, so that's the world we're dealing with here. Now, I'm going to ask, what does an HTM do? What does a cortex do? What does your brain do? You can summarize it in these 4 points. The first thing it does, and this is the most important one, it has to discover the causes in the world. When you're born, you do not know about the things in the world. You do not know languages. You do not know English. You do not know rooms or MIT or Kresge. You don't know about technology review. You don't know diddly squat. Your brain is like an empty thing, and at least the cortex is. And it has to discover it. No one programs it. No one puts it in there. And the only way it's going to discover it is through its senses. There is no other way. It has to look at these weird patterns coming in and on its own discover what are the causes in the world. This is what we do as intellectual beings. Science is all about discovering causes. There are low-level causes and high-level causes. And we like to, and the smartest people discover the highest-level causes. They find out, why is this thing happening in my world? Why am I experiencing these things? Well, scientists do it, business people do it. They just try to discover causes. Nicholas up here, he's trying to discover the causes of problems in the world and thinks he can solve it with education through low-cost laptops. Perhaps he's right. But it's discovering causes is really sort of the pinnacle of what brains do. Now, once you've discovered causes, and I'll tell you how we do this in a minute, once you've discovered causes, and as you do it, you can now infer what are the causes of novel input that are coming in. So inferring is a fancy word for sort of pattern recognition, but it's a little bit better than pattern recognition. If I show you a picture, and instantly you'll know what it is. Like here's me say, it's a gorilla, that's a helicopter, or whatever. You can do that in 300 milliseconds. You're very, very fast at it. But that's, you basically, I show you something, you infer, oh, what was the cause of that? You look at a room, you say, oh, I get that. Anyway, inference is essentially taking novel input, something you've never seen before. Never seen before. And by the way, every moment of your life you have novel input. It's never repeating. And you basically want to assign it to some causes. You say, okay, I think I know what's going on out there. So I've discovered the causes, now I infer my new input, what's causing it. The third thing is that the brain and HTMs model the world so they actually can be able to predict the future. They actually know given what the current input coming in and current state, current set of beliefs, what is likely to happen next. You're not aware of this, but you do this every moment of your waking life. You're constantly predicting what you're going to see next, hear next, and feel next. You do this at low levels, such as when you put your foot on the floor, or when I touch this podium, which is a novel thing. I've never done it before. I have expectations. If my hand went through the podium, I'd be very surprised. I make these predictions all the time, and we do it at high levels. We predict what's going to likely happen at a conference like this, when we try to predict, is Nicholas going to be successful with his $100 laptop, and so on. And then finally, it turns out that you can... that motor behavior is actually an offshoot or a derivative product of prediction. And the cortex is responsible for all our high-level motor behavior. Mine's speaking, yours is listening right now. But it's part and parcel of that. And this is going on throughout the neocortex. In my talk, I'm going to focus on the first two of these. I understand all of them very well now. I'm just going to have time to talk about the first one. How does the system discover causes? How does it do inference? And then at the end of the talk, I'll talk about HTMs and Numenta and what we're doing. So here's a picture of what we're trying to accomplish. We have some box with some question mark in the middle of it. We have some sensory data coming in, and we want to have a set of beliefs coming out the other end. And all I want to point out is that people have been trying to do this for a long time. People have been trying to come up with systems that discover and infer causes, and it's proven to be a very, very difficult problem. Today, there is no computer in the world that you can show it a picture of anything and say, what is this? Not even close. Not even close. You do it in 300 milliseconds. I can show you 3 pictures a second, and you can recognize it and know what every single one of those is. You do it so easily, so fast, we have nothing, no computer that can even come close to this for any number of objects. It's proven to be a very, very difficult problem, but obviously brains do it in a very simple and fast way. Otherwise, we couldn't do it so reliably and so quickly. We don't have any computers that can do understanding language, really understanding it. There's no real true machine learning algorithms out there. It has been a hard problem. And I think I know how the brains do this, and the HTMs do it, and I'm going to show you. So I'm going to tell you what's in this box right now. Let's open it up, and if you look inside, you'll find out that inside there's actually a hierarchy of connected nodes. It turns out that in the neocortex, the different regions of the neocortex are connected in a hierarchy, just like I'm showing here, but this is a schematic diagram. This is to help you understand the picture. At the bottom of this hierarchy, I have my sensory data coming in, and at the top of the hierarchy, I still have my output, which is a set of beliefs about what it is I'm perceiving at this point in time. But notice I actually have a set of beliefs along the way. It's a hierarchy of beliefs. And this is like a tree-shaped, an inverted tree-shaped hierarchical belief net, if you're familiar with probability theory. Now, what I'm arguing is that inside of this whole system, these little boxes, each one of them is a node. And each node is connected in this hierarchy. Each node is doing the same thing. Each node is actually discovering causes in this world and making predictions and doing inference. Each of the little boxes in the hierarchy is doing that. Now, obviously, if I have a box at the bottom of the hierarchy, it's only looking at a small part of the sensory input space. So a node at the bottom here is just looking at a teeny part of your visual space, or a small frequency range, and so on. And then at the top, you have a belief about the entire thing. So although each one is discovering causes, they're doing it for a different part of the sensory world. Now, a low-level module here will send up its set of beliefs, like a probability distribution, to the next level. And the guy up above will be looking at multiples of those and then converging and so on going up. And they also pass predictions down. Because you'll see in a moment they all learn sequences, they can predict what's going to happen next, and that becomes like a prior in the terminology of probability theory. So I'm now going to answer two questions about this. One question is, why does the hierarchy make a difference? And then two, how does a node in the hierarchy discover causes? Because I still have to explain how that happens. And then I'll show how this thing works, actually show you some results, and then how we're building it. So let me go down 2 points. Why does the hierarchy make a difference? The most important part, well, they're all important, but this is number one here. We can use a technique called belief propagation, which was invented by a guy named Judea Pearl. And belief propagation is a mathematical technique that was designed for AI, which says if I have some different beliefs, I have different nodes that represent beliefs, there's a way that if I impose a set of beliefs on some set of the nodes, the other ones very quickly form a belief that is consistent with that. So in this case, I can put a pattern at the bottom of the hierarchy, force a set of beliefs on the lowest level nodes, and all the higher level nodes will very quickly say, what is the most consistent belief I could have consistent with those inputs below? Let me give you some examples of how this might be useful, or how it is useful. If I would ask you what this figure is on the picture, what shape this is, you'd say it's a square. But if I ask you to define what a square is, you'd say, well, it's got straight and horizontal lines, it's got 90-degree corners, and so on. Anything you define a square is not in this picture. This picture isn't of a square. It's actually of this little thing that has these little diagonal lines all over it, but we see it as a square. And this is the kind of thing which I'm using this as illustration of the kind of things that trips up machine vision systems. Now, if I had a little region of my hierarchy that was only looking at some subset of this component, it wasn't looking at the whole thing, and it's trying to infer or discover the causes, and it's trying to infer what causes are there, it sees this little piece in the circle and says, well, I'm not really sure what this is. This doesn't look like anything I'm familiar with. It might be a diagonal line because I see some diagonal stuff in it, and it might be a vertical line because I see some vertical orientation to it. And I'm going to give you a distribution of beliefs. I'm going to say it's most likely a diagonal line. Maybe it's a horizontal line or something else. And it really doesn't know what's going on. The next guy up in the hierarchy is looking at a whole bunch of these and says, what kind of belief could I have which is consistent with all these possible beliefs below me? And he says, well, the only one that makes sense is if I can assume that they're sort of vertical lines, and I'll ignore the primary hypothesis that they're diagonal lines. And it gives you a sense that when in a hierarchy, these guys get to resolve themselves. This is what belief propagation does. Another example is the following, when you have an ambiguous character such as this H, but in context you have no problem seeing what it is. The ambiguity gets resolved by the surrounding information. So belief propagation. We actually use a modification of belief propagation, but it's similar if you're familiar with that technique. The next thing is the hierarchy lets you share representations. This is key for two reasons. It allows for generalization and for efficiency. What I mean by shared representations is when I have a representation for a cat at the top or a dog at the top, they share a lot of common components. They may be both furry, they may be both feet and ears and tails and things like that. And so when you train these systems, it turns out that you reuse components that were learned earlier, and allows you to generalize. So if I see a new animal I've never seen before, and I see it as fur, I do not have to say, what is fur? I've never seen this animal, therefore what is it? I can say, oh, I know what fur is, I know what heads are, I know what eyes are. And you basically, the system is able to generalize and have predictions about novel inputs it's never seen before. And then finally, it's an efficiency argument, because many systems, when people try to scale them, they don't work. They run out of memory, they have computational explosion problems. In this case, we are sharing representations, and you can scale these systems to be very large and recognize and understand many things because they're sharing things in a hierarchy. The next component of this is that the hierarchy affords a natural mechanism for attention. And I don't want to get into the details of this. I wrote a little bit about that in my book. But we attend to things all the time. We don't look at the entire scene all the time. We attend to some component of our visual field. We listen to the oboe in the orchestra. We listen to someone's particular voice. We're constantly doing attention, even though I have this very massive input coming in. And the hierarchy provides a very simple way of routing information, so I only attend to some portion of that input coming in. And the next thing is, I'm going to get two more of these on this part. The next thing is that the world turns out to be sort of hierarchically structured. And that matches the way the hierarchy works in the HTM or in the cortex. Just to give you an example, imagine I was trying to find a correlation between two parts of my visual field. And I say, I want to find a correlation between things that are happening over here and things that are happening over here. Well, it turns out that mathematically there'd be very little correlation between those two things. Very rarely, you wouldn't be able to find it. But if I ask about two things that are very close together in your visual field, there's a very high correlation between them. So there's a natural sort of, let's find local correlations and then larger correlations and larger correlations. Similarly, when I look at things like, take a thing like a person. People have bodies, torsos, legs, arms, and heads. And then each of those has substructures. So my head has ears, eyes, nose, and mouth. And each of those has substructures. And it turns out that that's the way the world is set up, and that's the way the hierarchy is able to capture it. It finds local structure first, and larger structure, and larger structure. And finally, I'm going to make the point, I write about this at length in the book I wrote, but each node in this thing actually stores sequences of patterns. This is a memory system that's inherently temporal. And when I say a sequence, I mean like a song. You can imagine like a little song. So you're a node in this hierarchy, and you see these patterns coming in. You want to learn the most logical and common transitions through time. And what you do is you pass to the guy above you, you pass a belief about the name of the sequence, not the details. It'd be like saying, I'm hearing a song, I'm going to tell you the name of the song, my belief of which song I'm listening to, but I'm not going to tell you the details. Now, the advantage of this is you have very fast-changing patterns coming in at the bottom, like my speech, which is a very fast-changing pattern. And as you go up the hierarchy, time gets condensed, condensed, condensed. And at the very top, what you want to have is the highest level representations. You want slow-moving things. You want to not listen to my phonemes. You don't want to listen to the words I'm saying. You want to be thinking about the concepts coming out of what I'm talking about. So there's a natural sort of coalescence of time going up. Similarly, you can take a very high-level pattern at the top, and as you pass it down, it unfolds. The sequences unfold. So I can say, Jeff, give a 45-minute brain talk, and then I do this for 45 minutes. It just kind of flows out the bottom, a very complex temporal pattern. So that's it. So the next question I want to ask, so that's why the hierarchy makes a difference. Now I'm going to talk about how does a node discover causes? What are the methods it uses to do this? Now, think about this. A node is looking at some pattern. It doesn't know, part of your brain. I say node is a node in an HTM. It's a piece of your cortex, okay? It's looking at a pattern coming in. It knows nothing what this pattern means. These are just cells. This is just some piece of software we've written. It knows nothing about the world. It doesn't know what these patterns means. How is it going to discover what's out there? Well, here's how it does it. It has only two things to work on. One is it can look for common spatial patterns, and the second, it can look for common temporal patterns. Let me explain what these mean. Let's say you were looking at I'm sorry. I have a slide here I forgot. When I say common spatial patterns, we're just talking about things that happen at the same time. So if I have pattern A occurs and pattern B occurs, and they always occur together, I can assume, being a little piece of cortex, I can assume that they're related. There's a causal relationship between them. They share a common cause. It's like if every time I see a dog and I hear a bark, I can say, hey, they are probably the same thing. They come together over and over again. They happen at the same time. That's a spatial pattern. If I was looking at a region looking at a very small piece of, say, visual field, let's say I was looking at 4 pixels in an image. So I have a 4 by 4 pixel patch, excuse me. So I have 16 of these little pixels coming in. Now, I'm just looking at a number of 16 inputs. I don't know it's a pixel patch. I don't know it's representing anything in the world. I just have these 16 inputs coming in. I'm showing it this way so you can understand it. But imagine I'm looking at a 4x4 pixel patch of an image, and I say, well, in that 4x4 pixel patch, if they're binary pixels, I can have 64,000 different patterns coming in. Well, some of them are going to be very common, some are going to be uncommon. I've shown a row at the top here, some things that might be common. You could assign those to, you and I could say, oh, that's a vertical line or a horizontal line or a corner. This system doesn't know that. It just says those things, 4 things happen together often enough. I'll assign a cause to them. And so I'll assume that when those things occur together, there's a common cause. There's many patterns which are uncommon. You won't see very often, maybe never see, and we just want to assign causes to them. The next thing we do is once we have these spatial patterns, we look for common sequences between them. And let me just give you an example of that. Here's something similar. Now I have 3 sequences in time. So it's time going from left to right. And you can see in the top row here, I have something we would say is a vertical line moving from left to right across this little patch of visual field. And if you see that often enough, you'll say, hey, those things occur in sequences like a song. I'm going to assume there's a common cause for them. And I'm going to learn to represent that. If those of you know any neuroscience, that's like a complex receptive field cell type. And the second row there, you can imagine is like a corner moving from upper left to lower right across my visual field. The bottom, I show an uncommon sequence, something you're not likely to see, a vertical line followed by a horizontal line followed by something else. So most of the inputs that are possible never will happen. And what a region of cortex has to do, and what a node in HTM has to do, it has to do these processes. And we do it in probabilistic framework. I'm not going to go through the math here today. I didn't think it was appropriate. But there's probabilistic techniques you use this. It's never clean like this. But essentially, this is what the system does. There's one more way that we discover causes, which is a derivative of the previous 2, which I thought was worth mentioning. People say, well, aren't you taught things? Doesn't your teacher, your parents teach you things? And I say, yeah, but they're coming through the same sensory screen just like everything else. It's just more of the same. But what happens here is, if one part of your hierarchy, like the auditory hierarchy, is hearing a representation, so someone is saying a word, you can associate it top-down onto patterns coming up from below. Let me give you an example of this. Let me take the concept of fruit. You have a concept of fruit. You have cells in your brain which respond to the concept of fruit. You know that word. It's a cause in the world. However, you know an apple's a fruit and a banana's a fruit. But there's no pattern you're ever going to see bottoms up visually that's going to tell you an apple and a banana are part of the same thing called fruit. They just don't transform between each other. And what it takes is someone telling you, saying the word fruit when you see both of those things. And so fruit is a common pattern that's in one part of the hierarchy, and it comes as a top-down influence, forces a common belief for those 2 things. So I just want to be complete showing this in this scheme here. But the first 2 concepts really capture the whole thing. So you might ask the question, does this really work? Is this guy just making this stuff up? Is this a bunch of baloney? Is this really true? And they do work. We've built this stuff, and I'm going to show you some of the results. I wanted to give a live demo over here, and I can do that on my laptop, but I didn't really have time for that, so I'm just going to show you some of the results of this. We built several systems testing this out. I'm going to show you a visual system, a very simple visual system, but still doing something significant. This is a visual system that has a 32 by 32 retina, if you will, and it looks at little drawings in a 32 by 32 world. We designed an HTM with 3 levels to the hierarchy, level 1, 2, and 3, creatively labeled here. The bottom level, there's 64 nodes. Each of those nodes is looking at a 4x4 pixel patch, just like I talked about earlier. And each of those creates a set of beliefs, the distribution, the probability distribution about beliefs of what it's seeing. We feed that into the next level. There's 16 nodes there. Each is looking at 4 nodes below it, and then there's one at the top. We trained this on a corpus of black and white line images. I'm not claiming this is an important problem. I'm just saying that we're solving a very difficult problem, and that it illustrates how the system works. So this is the objects that we trained it on, and I'll show you how we trained that in a second. And we basically wanted to discover these causes. These are the causes in the world we wanted to discover and do inference on. If this picture shows you a little bit how we do it. On the left column, you'll see 3 training images. We call them the helicopter, the dog, and the bee. And what we do is we take these images and we put it on the retina of the system. We move it around. You just literally slide it around. It'd be like a child holding an object in their hand and just looking at it like this. Time is very important. You can't learn to do visual inference without time. And this system can't learn either. You have to basically expose it to patterns through time. So we do that for all these different symbols, and then it forms beliefs about what are the causes in the world. And because there's 81 causes that I know about in the world. Then I show it new patterns it's never seen before. The second two columns show you some examples of that. We showed it can be different sizes, different orientations, and so on, some noise in them. Those are correctly recognized. The fourth column over, you see some inputs which were not correctly recognized. They were basically felt that it was something else. And that's in the last column. So that top row there, you see an input that says, no, I think this is closer to G. And you might forgive it for these mistakes. This is, if I were to run the software for you, I think it's important to get a sense for what's going on here. This is two screenshots from the software that's running. On the left side, we have an input pattern. This is a kind of corrupted dog. It's a dog with a swollen head with lots of holes in it. It has only one leg and no tail. It's very different than the dogs we trained it on. But we show it this pattern, and very quickly it comes back and says, well, here's my distribution of beliefs. It says, I'm pretty certain that this is a dog. And then you can see these are the pictures down below just telling what it was trained on. The next thing it says, well, it might be a little bit like a cat, and you can see the cat symbol sort of embedded in the dog symbol. The next one we call it the bus, and so on. You can see why we'd have these other beliefs that are slightly possible, although it's pretty certain it's a dog. If you do this for a lot of images, you see it's quite robust. Here's a picture that shows some of the results. These are all images that are correctly classified or inferred. And take a look at the left column here. You see these are all different dogs. You see it recognizes dogs facing left and facing right, and big and small, and so on. Look at the sixth column over, a thing that looks like a mug. And go down to the bottom. So I'm looking at the sixth column over in the bottom row. Now there's a symbol that, it's a bunch of bits. It's a lot of noise, actually. And you and I can see that that's a mug. And so does this thing. It sees that's a mug, too. This is a really hard thing to do in traditional computer vision. In fact, we don't know of any system that even comes close to the performance we're getting here. It turns out this is hard. If you ask, well, what's a mug? Anything you might define, a mug is not visible in this picture. It doesn't have straight lines, it doesn't have corners, it doesn't have the intersections. It's very, very, but you and I have no problem doing it, and neither does an HCM. It does this very fast and works, I believe, on the same principle that we do it on. So now I'm going to switch my talk. I'm not going to give any more evidence that this thing works, but we've done a lot of testing on this. I'm going to talk about Numenta and what we're trying to do at Numenta. I have a couple of goals. One is I want to maximize the impact of this technology. I think this is a huge technology. I'm going to talk a little about what you can do with it in a moment. To me, this is like the beginning of the computer era. This is a whole new paradigm of how you deal with information and how you might use technology to build products and to increase human knowledge and so on. So I'm trying to maximize this. I only got so many years left in my life, so many good years left in my life. I don't know how many yet. But one of my goals has been to build these machines and actually increase knowledge about the world through them. And I really want to maximize the impact of this technology. I think it's an enabling technology, and that's a goal of Numenta. Along those lines, and by the way, we decided to do this as a for-profit because I actually think I can maximize the benefit of this technology quicker as a for-profit than as a non-profit. The next thing we're going to do is part of this, we want to build a community of people. I'm here early. I'm not really out talking about this, but this is an emerging technology conference, so I said, okay, I'll come. This is emerging technology. I'll come and talk about this. Sometime in the middle of the next year, so the end of next year, we'll actually have product and be able to bring people in and have people start using this stuff. But we want to develop a community of people, whether it's researchers and scientists and commercial labs, students, you name it, people who are exploring this technology and seeing how it works. There's a lot of parameters in here. This technology is very robust. It sort of works no matter how you hook it up. Just like brains are very robust. And yet there's a lot of parameters you can tweak and experiment with. There's different algorithms you can use for learning sequences and spatial coincidences and so on. There's different types of problems you can apply it to. It's a very open-ended sort of problem. So we're not going to try to do this all ourselves. What we are doing, I forget my order of my slides here. Yes, what we are doing is we're building a software platform today that lets you build hierarchical temporal memories. And this platform includes sort of a supervisor and a net list and these nodes, and there's algorithms in the nodes, and then a set of tools that let you configure the networks, train them, and debug them. And there's a lot to this. If you want to attach it to a new type of sense and so on, there's a lot to be done. We're creating this framework. We think these networks can get very, very large. In the human brain, there are something like 300 million cortical columns, which is sort of equivalent to a node here. 300 million. And we think we can build brains that are bigger than that. And we're trying to architect this system for very large systems. And so from the very get-go, we're creating a highly multiprocessor implementation of this. And I won't go into details of that, but that's just pointing out we're trying to create this environment where people can create very large and sophisticated HTMs and experiment with them. and apply them to problems. So what might you do with this? What's it for? What are you going to do with it? Well, I already told you the 4 basic capabilities before. Discovering causes in the world, and we have one world we live in, but HCMs can live in other worlds. Discovering causes, doing inference, making prediction, and creating sophisticated robotic behavior. All things that people have been trying to do in AI for many years, but with some or less success. One thing that's worth pointing out here is that we can go beyond biology in many ways. We can make these systems faster. Neurons and silicon are about 1 million-fold difference in performance. And so brains are actually made of really slow components. So we should be able to get these things to run a lot faster than biology. We can make them larger in various ways. We can make them broader and deeper in the hierarchy and so on. And there's a lot of possibilities here. I like to point out that Einstein's brain was just like your and my brain, just slightly different. He had a regular brain. He had a cortex. It worked on the same principles. It wasn't something completely different. He was just at the extreme in some dimension. We don't know what that dimension was, but it's just marginally different. And in the promise is we can actually make machines that are much smarter than humans. I'd like to take this point to say that we're not trying to create humans. This is not about building human-like things at all. There's no emotions in these systems. It's not like they're not self-reproducing. They're not robots. It's not C-3PO or anything like this going around. These are things that sit in boxes on shelves that churn away on problems. So I don't want anyone to confuse that. But we can make machines that are really smart in various areas. And of course, we can extend beyond the senses that biology has afforded us and into many exotic senses. You might ask, well, what can I do with this? The simplest thing to do is to say, well, anything that humans do easy and computers don't do very well at all is a good candidate for this. That's a very simple filter on this. So, whether it's machine vision and language and robotics, there's many applications from security to self-driving cars. We've had all kinds of people come to us who've read my book and followed our work in suggesting many different types of applications that are sort of very today and obvious type of applications. You can extend these obvious applications with new sensors, whether it's infrared or sonar or radar. It really doesn't matter. The system works as long as you have the right type of data and the right type of sensory input to it. What makes me most excited about this is that you can apply this technique to very exotic worlds and exotic senses. It's a very generic technique. I had an oil exploration company come to me who have tremendous amounts of geophysical data, underground geophysical data, and they don't really know how to understand it. They don't know how to find what they want to. They didn't know this, but the term they really want to do is find out the causes for that data. And if they can find out the causes, they might be able to predict where oil is or how much oil they're going to get out of that. But it's just a mess for them. They don't know how to interpret that today. It's a perfect example of the kind of data that HCM should be able to look at and say, I can infer what's going on here. In my book, I use the example of weather, which might be helpful for you. The weather stations in this country are like a big retina. There's little points of weather monitoring all around this country. And it's like a big retina. And you can take that input and feed it into a bottom of an HCM, and it will infer the causes of it. What are the causes of weather? Well, there's storm fronts, and there's storms, and there's things like El Nino. Perhaps there's higher level causes. What are the real causes of global warming? How are we going to find that stuff out? These systems can crank away at this tirelessly, very fast, in very large capacities. People obviously apply this to understanding markets. I'm interested in understanding things like cosmology and physics, even genetics. How does a gene express the phenotype? These are kind of problems where there's the right type of data, and you're trying to discover the causes underneath it. It's what scientists do. And these systems will do very well at that, I believe. If you want to know more about this, there's only 2 things you can do right now, unfortunately, other than try to grab me afterwards, perhaps. But you can read my book. I don't really care if you buy it. Just go get a copy from the library or something. But my book actually talks on intelligence, talks about this in quite a depth. It's more on the biology side. It gives the overall theory, and it talks about the biology. It does not have the math, because remember, I didn't know the math at the time we did this. I didn't know how to build it at the time. But the last chapter in the book actually talks a lot about how I think this is going to play out as a technology and as a set of industries. And if you're interested in that, you might want to read that. The other thing you can do is you can go to the Mentis website, which doesn't contain much information, but allows you to put your name on a mailing list. And sometime next year, we hope to have some white papers out. We'll notify you about that. And we'll also be announcing when we have our first developer symposium and so on. So that's the end of my talk with the cryptic thank you at the very end there. And I think I'm ready to take talk. I'm taking questions here. Do I have time for questions? Yes. Because we don't have a clock here. Okay. No, oh, thank you.
A fascinating discussion. Could you say some more on the interconnects? So on your simple schematic, you show one node connecting to one node and up the food chain, but we all know that's not how the brain is, right?
Yes.
Every node is connected to lots of nodes, and all the information is in the interconnect.
Yes.
So how do you envision implementing outside of a network?
How do you implement these interconnects in physical systems?
Right. Could you give us some ideas?
Yes.
About
I mean, this is the problem. In fact, I talked about this in the book, and I didn't know how to solve it. You have a huge number of interconnects. Now, it's not everything's connected to everything. There's actually a very sparse interconnection. But you have so many nodes that even in a very sparse interconnection, you have a huge number of connections. The number of axons, which are the connections in a brain, is very, very large. And it occupies a large volume of the brain. So how do you handle this? In the end, way it gets handled, in belief propagation, you have two nodes that are talking to each other. These are like two regions of cortex talking to each other. In belief propagation, they form what they call a conditional probability table, which is it's basically a two-dimensional table where you have one set of beliefs coming on one axis, another set of beliefs coming on the other axis, and they show how the beliefs interact with one another. Now, it turns out that CPD, those tables, are, in a sense, the connections in the brain. They are very large in our systems. The CPTs are very large, but they're very sparse. And so we spend a lot of time figuring out how to represent very sparse arrays, very large but sparse arrays. That's how the connections get implemented. We have, in the HTM technology, we also have some clever routing mechanisms, how information gets passes between CPUs and so on. We try to do this very intelligently. But it is a problem, and we think ultimately the performance of the systems are going to be dictated not by CPU power, but by connectivity. But we think we have a way of handling it with these very sparse arrays and being clever about how to handle sparse arrays. Yes?
Two slightly related questions. You talk about discovery, inference, and prediction.
Yes.
Right now, based on your tests, your toy domains with these things, where do you think the greatest leverage is going to come from? You think these systems are predisposed to be better at discovery, inference, or prediction, or is that one of the research agendas? And related to that, you talk about exotic senses. Give an example of an exotic sense and to what extent that may bias the discovery, inference, and prediction forecasts that you're doing.
Okay. So the first question is, which of these are more important, perhaps? Discovery, inference, and prediction?
No, not necessarily. I don't care which one is more important. Based on the technology that you have, which is the likeliest to be superior or better?
Which is likely to be superior or better? I really can't answer that question. They're all happening at once. It's kind of hard not to do them all. And I don't have enough data to know, which one will be better at than humans. It's kind of hard to separate them out. It's like, it's very hard to separate them out. They're not really separable things. You have to do inference while you're doing discovery. Maybe I would like to say, to me, the most important thing is actually discovery of causes, which is, I want to understand how the world works, right? And I want to understand, what the nature of time is and genetics and so on. And that's all discovery of causes. I think to me, that's the most exciting part of it. I'm less interested in the robotic sense of it, for example, but that's going to happen. Your second question was interesting, and I've forgotten it now. Exotic senses. I gave you one sample of an exotic sense. I would include the weather stations as an exotic sense. Let me throw out a really interesting tidbit. This is a technical crowd, I assume, right? Brains are two-dimensional surfaces. The cortex is a two-dimensional surface. We work in more than a two-dimensional world. And so we have to somehow we have to discover the causes in a or you might argue, a four-dimensional world if you include time, but at least a three-dimensional world, and we represent this in a two-dimensional sheet. It's actually not an efficient way of doing this, but it's just the way nature stumbled upon. And if you understand the HTM algorithm, there's nothing inherent about it being any particular dimension. And you can actually design the system with the connectivity scheme that it could be thinking in 4 dimensions or thinking in 6 or 8 dimensions. It doesn't seem to really care. Brains can't do that, but these systems can do it. And so I think about exotic senses, trying to imagine things in high-dimensional mathematical spaces. You could design, basically feed it data, which is a sensory system in some sense, whether you're generating on a computer or actually having a real sense. You're feeding it sensory data of higher dimensions, and the things can work on it. It can get pretty exotic, and that's why I used the word exotic in that. Yeah, and I'll get to you next. I didn't know who's standing first, so, okay.
We've discussed how things can be discovered, causes can be discovered. Sometimes they are erroneously discovered. How does an HTM unlearn, rebalance the probability tables, and pick another direction?
Very good question. In fact, Here's how I view it, right? There's a lot of humans on this planet, 6 billion or something like that. We share a lot of common experiences, low-level experiences. We all share gravity and light, the sun, the moon, trees, and so on. And we've all formed a set of beliefs. Beliefs are just beliefs. They're not the fact. They're beliefs. Our model can be good and can be bad. And we generally have a fairly good set of beliefs at the lowest levels in the hierarchy. And they pretty much represent the world as it is. And we share them. But when you get to the higher level causes, we don't. And we often have very different beliefs. You see this in religion. You see this in all kinds of politics. And this leads to the conflicts in the world. And we have false beliefs. There are many things that people believe. By definition, if we believe different things and there's one world, there are many things that are false. So I think it's an inherent problem in the system that you can form false beliefs, and it has to do with the quality of the data and the sensory systems you're working with. When it comes to things like religious beliefs, for example, which it's about stating an opinion, saying at least some of them are false because they can't all be correct, then how do we know this stuff? Well, we're not getting them primary data. We're getting them secondary, tertiary data. We're getting someone telling you something and so on. And so we start forming false beliefs about things. So this is an inherent problem in the system, but I think it's one of the beauties of this, if you just force the system to rely purely on real, it's a matter of data. If you give it the right sensory data, it should do a very good job and should not form false beliefs. How do you correct it? The only way you can correct it is just by showing it good data. That's the only way of doing it. You have to show it conflicting evidence, and it'll relearn. Humans are relearning all the time. Our brains are very plastic, and we will form new beliefs about the world very rapidly in a matter of hours if you just present the right data quickly. So I don't know if I've adjusted the system completely. Obviously, this is a problem. You could create a system that drives a car or flies an airplane, and it might have a set of false beliefs, and that wouldn't be good. And that's a problem we'll have to deal with. Yes, this gentleman over here.
Thanks. Along the similar lines, I guess my interest is if you replace these nodes by humans, during your thinking on this, hierarchies have gone out a bit in a networked world. Did this tell you anything or give you any insight about how humans as groups learn?
The question is, does this model tell us anything about how humans as groups learn? I haven't really thought about that, and I have to admit that. I've thought a lot about how humans as an individual learn and how this theory impacts that. And I've had quite a few people who've written to me from psychology and in other fields about this. But I haven't thought about that. I'll answer a slightly different question, and maybe my time is up. Can I answer this question? Yeah, I'll answer this question. There's a bunch of people in the world, not many, who are interested in complex systems. And complex systems are systems made of lots of individual elements that seem to produce a sort of Uber behavior of some sort. Examples of complex systems are ant colonies or any colony type of insect, markets, and brains. Brains have been always an example of a complex system because all these neurons, none of them know what's going on, but somehow the whole system seems to do something pretty neat. I asked myself, can this theory tell me something about complex systems in general? So societies are complex systems. And I think the answer is yes. I think there's a general theory of complexity that can come out of this work, which I'm not prepared to talk about today, but I'm spending some time thinking about. And I think by exploring how HTMs work, we will actually learn a lot about how other complex systems work, because they share a set of properties that lead to this behavior. So I haven't given that specific question thought, but I have given sort of the Uber question about what can I learn about complex systems, and I think it tells you something about that. And we'll have to see what that is going forward. Thank you again very much.
Gentlemen, Jeff Hawkins, thank you very much.
Thanks.
Thank you so much.